Hello, welcome to this first video to accompany the Further Maths Conference calculus session. In this first video, we're going to look at one of the activities that you can use to help your students see some more interesting ideas around calculus. And this activity is around Gabriel's horn, which uses some of the ideas from volumes of revolution and improper integrals, but applies them in quite an interesting way to create a really quite surprising result. So the idea behind Gabriel's horn is it starts with a graph of y equals 1 over x, and then by taking the part of the graph from 1 all the way up the x-axis and rotating that around the x-axis, we get this shape. And we're going to look at both the volume and the surface area of this shape created by revolution. And then we're going to look at what happens if that is extended all the way to infinity. So, first thing, and this is something students should hopefully be comfortable with, we can calculate the volume of revolution. So we're going to start with just thinking about the shape itself here up to some point A, and then we'll look at what happens as A tends to infinity. So we're going to look at the volume of revolution as we go from 1 to some point A further up the x-axis. And we're going to get a volume which is pi lots of the integral from 1 to A of 1 over x all squared dx. This is pi lots of the integral from 1 to A of x to the negative 2 dx, which is pi lots of x to the negative 1 over negative 1 evaluated between 1 and A. And this whole thing then will equal pi. If I substitute in A, I get minus 1 over A, and if I substitute in 1, I get minus 1 or plus 1. This could obviously just be simplified a little bit to say it's pi multiplied by 1 minus 1 over A. So that's the volume from 1 to A, from here to here. Now I can think about what happens if this value of A tends to infinity as an improper integral. So to do that, I can say that this volume, pi times 1 minus 1 over A, I can look at the limit as A tends to infinity of 1 minus 1 over A. Well, 1 over A will tend to 0. This whole thing's been multiplied by pi, so this will equal pi multiplied by 1, which is pi. So we get the interesting result that this infinite shape, created by revolving around the x-axis, has volume pi as A tends to infinity. Now we can look at the surface area. Well, surface area is beyond the spec for students, but this is the integral that will give the surface area of revolution. I wouldn't expect students to learn and know this, but it's an integral that they should be able to work with. So let's have a go at doing this integral. And we get that the area is 2 pi. Again, we're going to go from 1 up to A to begin with, and then think about what happens as A tends to infinity. 2 pi times the integral from 1 to A, y is 1 over x, multiplied the square root of 1 plus, we need to know what dy by dx is, differentiate x to the negative 1, reduce the power, and bring the power to the front, and we get dy by dx is negative 1 over x squared. So I've got negative 1 over x squared dx, and all of this simplifies to 2 pi multiplied by the integral from 1 to A, 1 over x, square root of 1 plus 1 over x to the 4. Now this integral's not an easy one to do. there's no obvious way of evaluating this integral here. So we're going to use a technique that we're interested in what happens to this area, and I can show that I don't know what this integral is, but I know all of this in here is bigger than 1. So I'm going to show that the whole it's bigger than something that tends to infinity, and therefore it tends to infinity. Let's have a look at that in practice. This is our integral that I'm wanting to evaluate. I can't algebraically do this integral. What I can say though is that if I take 1 plus 1 over x to the 4, this whole thing here is greater than 1. If I take the square root of it, then it is greater than 1. If you remember, our x values are going from 1 up to here. This thing is some number, some positive number, so this is greater than 1. Therefore, I don't know what my area is, but it's found by an integral, and that integral is bigger than this thing, 2 pi integral from 1 to a. I can replace the whole of this with 1, and I get this relatively straightforward integral, which I can then evaluate, because this is just the natural log of x. So I get 2 pi multiplied by the natural log of x between 1 and a, which is 2 pi ln a minus 2 pi ln 1, but ln 1 is 0, so it's 2 pi ln a. Now this gives me something that I can think about what happens as it tends to infinity. I know that my area is bigger than 2 pi ln a. I can look at the limit as a tends to infinity of 2 pi ln a, and this thing is going to tend to infinity because the natural log tends to infinity very slowly, but it does tend to infinity. So I know as a tends to infinity, my surface area is bigger than something else that tends to infinity. Therefore, I can say that the surface area tends to infinity. All of which gives us a very surprising result, which says that as a tends to infinity, the volume tends to pi and the surface area tends to infinity. What that means in practice is we've created a shape here where the volume is finite and the surface area is infinite. That means we could fill it with a finite amount of paint, but we couldn't paint it. Which is a very bizarre result. If you want to find out more about this, have a look at the Wikipedia page for Gabriel's horn. But I think it's a very nice example of something you can show your students as an interesting application of both improper integrals and volumes of revolution.